All right, another important aspect of understanding material and matter around us is what we call mass and weight. Now, matter is what we call anything that has mass, and sometimes there's a little bit of a misuse of the term weight, right? Weight is a result of a mass having a force on it, and usually that force that we're familiar with is the force of gravity. So when mass is attracted by gravity, we call it weight. But the preferred way to refer to the how much of a material we have is its mass. Okay. Living on the moon, for example, sometimes you think of weight. We say, "Hey, I'm on a diet. I'm going to lose some weight," right? And so if you're on the moon, right? So here's the Earth, and let's draw the moon. It's a little bit smaller, right? If you're on the moon and you're standing on a scale, right? So here's me on a scale. I'm on the moon, right? And let's say it says I weigh 100 pounds on the moon. Well, if I were to come to the Earth, it would say I weigh 600 pounds on the Earth because the Earth's gravity is about 6 times as strong as the moon. Okay, so we lose weight when we go to the moon, but our mass is the same. Well, how could you differentiate the mass, right? How can we identify our mass? Well, here, if I am on what we call a balance on the Earth, right, and I'm standing over here, and I would need over here a weight of 600 pounds if I'm here on the Earth to balance me out, right? If I go on the moon with a balance, I'm here on the moon, right? How big would my mass need to be?
Um, you're trying to trick me. I'm sure it's just 600 again.
That's right, it is. It's 600, right? We might want to say, oh, it's going to be 100 because we're on the moon. But here, there is a force from the moon that's pulling down. It's not as strong as the force on the Earth, but it's pulling down the same amount. So a balance allows you to identify your mass, whereas a scale, which relies on the compression of a spring with the gravity, will just tell you your weight. Does that make sense?
Yeah, I get that.
Okay. So, another important concept of chemistry is what we call the law of conservation of matter. All right. In a chemical reaction, and in a physical reaction as well, you don't lose or gain matter, right? Or mass. All of your material is there some way. It's not increasing or decreasing. Okay. Um, so if I make some uh, carbonated beverage by fermenting some sugar with some yeast, right? Before and after, the masses of my material will be exactly the same. All right. I have a battery that's charged and one that's discharged. Again, before or after, the batteries will have the same mass. Now, this was difficult for people to pick out early in the days of understanding the world around them. They would create a tree and they would see mass just come out of nowhere, and they couldn't figure out where that mass was coming from. They would burn wood, for example, and the wood would seem to disappear to a significant extent, and they couldn't figure out where things were going, right? But with careful observations and scientific work, they were able to identify that there is no decrease or increase in mass as chemical or physical processes occur. All right, now let's talk about the elements. Elements, there are, more than 100. Um, it varies in terms of, the way that you think about it, right? I mean, right now we're about at 119, I think, right? But in terms of the ones that we're consistently utilizing, it's relatively few of these. Many of these higher numbered ones are synthetically made in the lab, and they only have very short lifetimes. So they might only exist for a few moments, right? So, but these are the Legos. These are the pieces that we have to make anything that we want to make in the universe, right? These are all of them. Okay. Um, Oops, other way here. There we go. We probably have an idea of what an atom is in our mind from previous classes, and if you don't, it's something like this. We have a nucleus that has protons and neutrons. with electrons on the outside. Now, this isn't a perfect model here, but it's a model that will work. But I have to show you a video about models. Okay, so here's a video that I want you to watch.
You're watching Nova Science Now video podcast.
Okay, so what do you think they were trying to show us with that video?
That the atom's really big compared to the nucleus.
All right, that's one thing. That's one thing that they were trying to show us. But we could have just said that the atom's really big compared to the nucleus. What else? What about models? What are they trying to show us about models or tell us about models?
Our understanding's not always right.
That's right. Our understanding is not always right. Um, the other thing that I think they're trying to let us know is that models are models, and we don't want to get stuck in the model, right? We want to know that when we say an atom looks like this or behaves like this, that those are models that we use to help us. But when we find something that doesn't fit our models, we don't want to just all of a sudden say, oh, well, then we have to be wrong, right? We want to make sure that we don't get ourselves stuck in the model. We allow ourselves to, to think more about things and use the models, okay? So, if we were to show, for example, a picture of the atom right here in the appropriate sizes, it wouldn't make any sense for our eyes, right? We couldn't see anything. We couldn't see the distance between the nucleus and the electrons and so forth, okay? All right, so that is an atom, a collection of protons and neutrons in a nucleus with electrons, and these are called subatomic particles, smaller than atoms, protons and neutrons and electrons. A molecule is two or more atoms together connected through what we call bonds, all right? And when there are these bonds, then these new elements that come together form new species that have different properties, all right? Those are called molecules, okay? Another word that we use almost synonymously as molecules is compounds, okay? Now, we have to have a conversation about the difference between compounds and kind of molecules. And here's that, okay? Here's a diagram that identifies all of the compounds that we have in our understanding, right? And within all of these, all the different compounds that exist, there are molecules, and then there are ionic compounds. So it's good to think, or easy, nice for us to classify all molecules as either, sorry, all compounds as either molecules or ionic, or molecular. We could say molecules are molecular or ionic. All right. And now to distinguish between molecules and ionic compounds, molecular compounds and ionic, molecular compounds contain only non-metals. All right. Whereas ionic compounds, for now, our definition will say that they contain a metal. All right. And some of our, and we'll go back here to the periodic table, some of these elements are metals and some are nonmetals. See this element here, number 5, it's purple, and it forms with these other purple elements here. I mean, it's not purple, but it's shaded pink here. A staircase. And this staircase separates the metals from the nonmetals. This side over here, these are our nonmetals, and all of the rest over here are our metals. Hydrogen is an exception. Hydrogen is a nonmetal as well. All right. So we can recognize whether a compound is molecular or ionic if it contains only nonmetals. So that's these ones up here. Then it is a molecular or a molecule. If it contains a metal, then it is ionic. Okay. Some of our elements are even molecular. Now, what that means is, for example, hydrogen, it doesn't go around singly, it goes around in pairs. So it's elemental, but because it's combined with another atom, hydrogen, the element hydrogen is molecular. Same with oxygen, phosphorus, sulfur, chlorine, bromine, iodine. All right. So nitrogen, I don't know if I mentioned nitrogen. These are molecules, or these are elements that are molecular. And it's important for you to remember this. And as we go, you guys will gather this because you'll see how they're expressed in chemical reactions as diatomic. We call it diatomic. 2 atoms coming together in its elemental form, in their elemental form. All right, so here's an example of a molecule. That's water, right? Here's another molecule, carbon dioxide, all right? Now I can go back to my periodic table here and see that carbon, is that a metal or a non-metal, Fred?
It's a non-metal. It's to the right of the staircase.
Very good. And carbon and oxygen, carbon dioxide, right? We're looking at CO2. Is oxygen a metal or a non-metal?
I see it over there. It's a non-metal.
That's right. So carbon and oxygen are both nonmetals, and that's why carbon dioxide is an example of a molecule, or we can say carbon dioxide is a molecular compound. Looking at the chemical formula here for glucose, and now we haven't talked about this, but this is probably something that everybody knows. Carbon, hydrogen, and oxygen are the elements here. 6 carbons, 12 hydrogens, and 6 oxygens. That's what this chemical formula means. Is glucose molecular in nature?
What do you mean molecular in nature?
Is this a molecule?
Well, yeah, it says molecules.
That's right, it says molecules. How could we tell if it didn't say, if we just had that chemical formula?
We could look at our periodic table.
That's right, let's look at our periodic table here. And we can see that carbon, oxygen, now is hydrogen?
Yes, hydrogen it's a molecule, or sorry, it's a non-metal. So this is a molecular compound.
Okay, very good. So we can use the periodic table to identify, and the chemical formula to identify whether any chemical is molecular or not. Okay, very good.